Today I'll be explaining the mathematics behind decryption techniques used in RSA encryption and the program in which I coded these methods. First, I'll be introducing the RSA cryptosystem and its mathematical complexities. Then, I'll be explaining different decryption techniques in RSA encryption. And finally, I'll be explaining a project that I undertook this year in which I used the programming language Python to code the decryption techniques that have been used to try to break RSA. RSA encryption was created in the 1970s as an asymmetric or public key form of cryptography that would replace the then commonly utilized and weakening symmetric cryptography. In symmetric cryptography, if two individuals wished to exchange secret messages, they would either have to meet beforehand to exchange identical keys or run the risk of their decryption key being intercepted. In a simplified example of symmetric cryptography, an individual named Bob wants to send a secret message to another individual named Alice. Alice and Bob would first have to meet each other to share identical keys that would be used for encryption and decryption so that each person possessed the same key. Then, Bob could encrypt his secret message using one of the identical keys and send the encrypted message to Alice, who would then decrypt the message using the other identical key that she and Bob had exchanged beforehand. If Bob and Alice could not meet beforehand to share identical keys, then Bob would have to send the key that decrypted his encrypted message, along with his encrypted message, to Alice, running the risk that a third party could easily intercept the encrypted message and the key used to decrypt it before it even came to be in Alice's possession. In 1970, James Ellis proposed a hypothetical idea in which secret messages could be exchanged between individuals without them having to meet beforehand to share identical keys, thereby eliminating dependence on the ever-weakening symmetric cryptography. The premise was simple. If Bob wished to send a secret message to Alice, Alice could create a lock and a key that decrypted or unlocked that lock. Alice could then send the open lock to Bob, who would proceed to encrypt or lock his secret message using the open lock. Alice would meanwhile retain possession of the key that decrypted the lock. Bob would then send his encrypted message to Alice, who would decrypt it using the key that had remained in her possession throughout the entire process. Such is the conceptual idea behind asymmetric cryptography. No keys must be exchanged beforehand, and no risk is run that a third party may intercept the key used to decrypt the encrypted message. But this was all conceptual. At least it was until 1977, when Ron Rivest, Adi Shamir, and Leonard Adleman created an algorithm based on James Ellis's conceptual idea about asymmetric cryptography that was henceforth known as RSA encryption. RSA has formidable strength, and as of yet, the only device that is considered to be capable of breaking RSA is a quantum computer. Rivest, Shamir, and Adleman's algorithm consists of 6 values that correspond to either a public or private key. The public key is released publicly and can be used by anyone to encrypt a message, while the private key is kept hidden by the key generator, the person who creates the public and private key values. The private key is used by the key generator to decrypt any encrypted message sent to him or her. The 6 values generated by the key generator are denoted P, Q, N, Phi N, E, and D. P, Q, Phi N, and D belong to the private key and are kept secret by the key generator, while N and E belong to the public key and are released publicly. The key generator must generate values for P, Q, N, Phi N, E, and D. The key generator must first choose 2 large prime numbers P and Q. In real-world utilizations of RSA encryption, these prime numbers are typically incredibly huge, usually hundreds of digits long, but for the sake of the example, I've chosen 2 very small prime numbers, 53 and 61. The key generator must then multiply these 2 prime numbers together to attain the value of n. That is, P times Q is equal to n. In our example, 53 times 61 is equal to 3,233. N is a semi-prime number, or the product of 2 prime numbers. Next, the key generator calculates the phi of n. The phi of a number outputs how many positive integers are less than that number that do not share any common factors greater than 1 with that number. For example, to find the phi of 9, list all of the integers less than 9 but greater than or equal to 1, 8, 7, 6, 5, 4, 3, 2, and 1. From this list, evaluate which integers share common factors with 9 that are greater than 1. 6 and 3 both share common factors greater than 1 with 9, while 8, 7, 5, 4, 2, and 1 do not share any common factors greater than 1 with 9. The phi of 9 is 6, because there are 6 integers less than 9 that do not share any common factors greater than 1 with 9. Calculating the phi of n is simple for the key generator, because the phi function is multiplicative, meaning that the phi of n is equal to the phi of p times the phi of q, or the phi of each of n's factors multiplied together. Thus, the key generator must calculate the phi of p and the phi of q, and multiply these two values together to attain the phi of n. This is much simpler than calculating the phi of n directly, because calculating the phi of prime numbers like p and q is easy. The phi of any prime number is simply one less than the original prime number, because the only factors that prime numbers have are 1 and itself. For example, the phi of 5, a prime number, is 4, because there are 4 positive integers less than 5 that do not share any common factors greater than 1 with 5. Thus, the phi of the semi-prime number n is p minus 1 times q minus 1. In our example, the phi of 3,233 is 3,120. To generate e, the key generator must pick an integer that satisfies the requirement 1 is less than e is less than phi n, and e shares no common factors with phi n. I've chosen e to equal 7 in our example. Finally, to generate d, the key generator must pick an integer that satisfies the requirement e times d mod phi n is equal to 1. The operation mod is short for modulus, and outputs the remainder of a division. For example, 8 mod 6 is equal to 2, because the remainder of the division 8 divided by 6 is 2. In our example, d is equal to 1,783. Once the key generator has generated values for p, q, n, phi n, e, and d, she must release the values of n and e, which are public key values, to the public, but retain the values of p, q, phi n, and d, which are the private key values. If a person wishes to send a secret message to the key generator, he can use the values of n and e to encrypt his message using the expression m to the e power mod n, where m is the secret integer message that is less than the value of n and shares no common factors with n that is to be encrypted. I've chosen m to be 89 in our example. The sender sends this encrypted message m to the e power mod n, the result of which is known as c, for ciphertext message, to the key generator. In our example, c is equal to 206. Because 89 raised to the 7th power mod 3233 is equal to 206. The key generator can then decrypt the encrypted message c by using the private key value of d through the expression c to the d power mod n. The result of c to the d power mod n should yield the original integer message m. In our example, 206 raised to the 1783rd power mod 3233 does in fact equal the original integer message m of 89. Eulers Theorem and a modular arithmetic exponentiation law can be used to prove that when the expression m to the e power mod n is used to encrypt an integer message m that is less than n and coprime to n, plugging the result of the simplification m to the e power mod n, which is c, back into the expression c to the d power mod n, will yield the original message m. Thus, Rivest, Shamir, and Edelman had to prove that m to the e power mod n, all raised to the d power mod n, is equal to m. For this, they turned to Eulers' theorem and modular arithmetic exponentiation laws. One law of modular arithmetic states that when a, k, and n are positive integers, and a is less than n, then a to the k power mod n is equal to a mod n, all raised to the k power mod n. In other words, a is equal to a mod n. This is because if n is a larger number than a, as specified by the law of modular arithmetic, it will divide into a 0 times. If n divides into a 0 times, then n multiplied by 0 will yield 0, so when 0 is subtracted from a remainder of a exists. Therefore, a mod n is equal to a. Because a mod n is equivalent to a, and when a is less than n, the expressions a to the k power mod n and a mod n all raised to the k power mod n are exactly equivalent. In turn, Eulers' theorem states that when a and n are coprime positive integers, phi n is Eulers totient and k is a positive integer, a to the phi n times k power mod n is equal to 1. Using Eulers' theorem and the law of modular arithmetic, we can prove that m to the e power mod n, all raised to the d power mod n is equal to m. In RSA encryption, m and n are coprime positive integers and m is less than n. Also, e times d mod phi n is equal to 1. Thus, e times d is equal to 1 plus k times phi n, where k is an increasing integer. I'll explain why e times d is equal to 1 plus k times phi n when I describe decryption through semi-prime factorization. The following is the proof of correctness for RSA encryption. If m to the e power mod n all raised to the d power mod n is the expression that we're attempting to simplify, then we can simplify this to m to the ed power mod n by the modular arithmetic exponentiation law. This in turn simplifies to m to the 1 plus k times phi n power mod n because of substitution, which in turn simplifies to m to the first power times m to the k times phi n power mod n due to properties of exponents. This in turn simplifies to m to the first power times 1 because of Eulers' theorem, which in turn simplifies to m. Therefore, we've accomplished what we've set out to prove. M to the e power mod n all raised to the d power mod n is equal to m. It is integral that the values of p, q, phi n, and d remain hidden and can only be accessed by the key generator, but releasing the values of n and e publicly does not detract from the strength of RSA encryption. This is because RSA encryption was built around two main assumptions that make it safe and acceptable to release the values of n and e publicly. First, it is exceedingly time-consuming to calculate the decryption key d by factoring large semi-prime numbers. Second, it is exceedingly time-consuming to calculate the decryption key d using properties of logarithms because of the discrete logarithm problem. If the decryption key d was accessed by a person other than the key generator, then this person would be able to intercept secret encrypted messages meant for the key generator and decrypt them using the intercepted value of d. RSA remains formidably strong because accessing the decryption key by semi-prime factorization or logarithmic properties both prove to be too time-consuming to be pursued realistically. What I've done this year is I've used the programming language Python to determine exactly how many iterations it would take to access the decryption key if I used the methods in either of these assumptions. Before I could get to any coding, though, I explored the mathematics behind these two assumptions and came up with formulas to determine the number of iterations needed to access the decryption key using either method, which I'll explain now. If a message interceptor, the equivalent of a hacker, wants to calculate the value of the decryption key using only the publicly available values of n and e, he has two options, the first being semi-prime factorization. When semi-prime factorization is used by a message interceptor to attempt to access the decryption key, the magnitude of the semi-prime number proves to be of paramount importance in preventing the message interceptor from calculating the decryption key. In the case of RSA encryption, the semi-prime number is n, the product of the two prime numbers p and q. The value of n is available to the message interceptor because it is a public key value. The message interceptor must factor the semi-prime number n into its constituent factors p and q. In our example, n is equal to 3,233, and we can calculate its factors to be 53 and 61 through a little trial and error. Then, the message interceptor can plug the values of p and q into the expression p minus 1 times q minus 1 to find the phi of n, which in our example is equal to 3,120. After the message interceptor has attained the value of phi n, he can plug this value, along with the public key value of e, which in our example is 7, into the equation e times d mod phi n is equal to 1, and solve for d. So how do you solve for d when the equation involves the operation modulus? The message interceptor knows that e times d must equal 1 more than phi n in order to achieve a modular relationship with 1 as a remainder. For example, if e is 7 and phi n is 3,120, then the formula would be 7d mod 3120 is equal to 1, and thus 7d must equal 3121 for the relationship to work. Knowing this, the message interceptor can easily solve for d. If 7d is equal to 3121, then d is equal to 445.857143, and so on. D, however, must be an integer value, so the message interceptor must look for other modular relationships that will yield a remainder of 1. For example, 6241 mod 6240, which is 3120 times 2, is equal to 1. Similarly, 9361 mod 9360, which is 3120 times 3, is equal to 1. The message interceptor can keep on multiplying the value of 3120 by increasing integers to achieve different modular relationships that will still yield 1 as a remainder, until d is an integer value. In our example, if the message interceptor multiplies 3120 by 4, he achieves a modular relationship of 7d mod 12,480 is equal to 1, so 7d is equal to 12,481, and in this instance, d does equal an integer, 1,783. Here, solving for d only required 4 iterations. The formula for solving for d simplifies to d is equal to phi n times phi n multiplier plus 1 divided by e, where phi n multiplier is a specific integer value that the message interceptor multiplies phi n by to achieve different modular relationships that yield 1. With knowledge of the publicly available value of e, as well as the value of phi n, the message interceptor can easily calculate the value of the decryption key d, because he has created one equation with only one unknown value. There is one small but vastly significant problem that exists with factoring semi-prime numbers. Factoring n into its constituent factors p and q becomes increasingly time-consuming as n grows larger. This is why large semi-prime numbers had to be chosen by the key generator as values for p and q. The larger n is the product of the already large values of p and q, the more time it will take to factor it. In RSA, the types of semi-prime numbers utilized are typically around 600 digits long. They're typically the magnitude of the number on the screen. That number is called RSA 2048 and is 617 decimal digits long. A number of this magnitude would take a huge amount of time to factor. In fact, in 1978, Rivest, Shamir, and Edelman predicted that factoring a 500-digit semi-prime number would take approximately 4.2 times 10 to the 25th power years to factor using the Schroeppel factoring algorithm. Therefore, because of the immense amount of time needed to factor n into its constituent factors p and q, it is vastly impractical for a message interceptor to use semi-prime factorization to calculate the decryption key d. The second option that the message interceptor has if he wants to calculate the value of the decryption key using only the publicly available values of n and e is to use the properties of logarithms. Recall that encrypting a message requires plugging a secret message m into the expression m to the e power mod n, and decrypting that message requires plugging in the result of m to the e power mod n, which is c, into the expression c to the d power mod n to attain the original message m. The message interceptor, like all others, has access to the public key values of n and e. He can generate a secret integer message m and plug it into the expression m to the e power mod n to attain the ciphertext or encrypted message c. In our example, I've chosen m to be 89, so the ciphertext message c is equal to 206. Then, he can plug in the value of c along with the public key value of n into the expression c to the d power mod n. The message interceptor knows that the result of c to the d power mod n must equal his original message m, so he can set c to the d power mod n equal to m. The message interceptor has knowledge of the value of n because it is a public key value, as well as c and m, because he is the one who generated these values. Therefore, the message interceptor has created an equation in which only one unknown, d, the decryption key, exists. In our example, c is equal to 206, n is equal to 3,233, and m is equal to 89. So the equation to solve for d is 206 to the d power mod 3,233 is equal to 89. Knowing that 206 to the d power must equal 3,233 plus 89, or 3,322, for the modular relationship to work, the message interceptor can set 206 to the d power to 3322 and solve for d using the properties of logarithms. If 206 to the d power is equal to 3322, then the log of 206 to the d power is equal to the log of 3322. D then is equal to the log of 3322 divided by the log of 206. D then is equal to 1.5218, so on. However, D has the restriction that it must be an integer value. Thus, the message interceptor needs to come up with another way to calculate D using this method. Similar to when he was solving for D through semi-prime factorization, the message interceptor knows that 3322 mod 3233 is equal to 89, but can use other modular relationships to his advantage to calculate D. For example, 3233 times 2 is equal to 6466. 6466 plus 89 is 6555. Thus, 6555 mod 6466 is equal to 89. So the message interceptors can set 206 to the d power to 6555 and solve for d. The message interceptor can keep on multiplying the value of n by increasing integers to achieve different modular relationships that will still yield m as a remainder until d is an integer value. The formula for solving for d in this way can be simplified to d is equal to the log of n times n multiplier plus m divided by the log of c, where n multiplier is the increasing integers the message interceptor multiplies n by to achieve different modular relationships that will still yield the secret message m as a remainder. Even though the message interceptor can keep on running this sort of sequence to achieve an integer value for d, the amount of iterations it would take to finally attain an integer value for d is astronomical, making calculating the decryption key through logarithms just as impractical and time-consuming as semi-prime factorization. This is because of the level of exponentiation required when solving for d using the logarithmic technique. In fact, when I ran this in Python, the amount of iterations required surpassed Python's programming capabilities, resulting in an overflow error. The difficulty of calculating the exponent d in this way is known as the discrete logarithm problem, or the RSA problem. In the case of either decryption through semi-prime factorization and decryption through logarithmic properties, an immense amount of iterations are required to finally attain the decryption key d. In the case of semi-prime factorization, if every integer less than the semi-prime number n and greater than or equal to 2 was tested to see if it divided evenly into n, the amount of iterations required would be n minus 2. If n is a huge semi-prime number that is hundreds of digits long, the amount of iterations required to factor n would be 2 subtracted from that huge semi-prime number. It is true that not all numbers less than n would have to be tested to see if they divided evenly into n if it was certain that n was semi-prime, because this would narrow the numbers that needed to be tested down to only prime numbers. But if access to a larger bank of prime numbers is not accessible, as was the case in this project, all the integers greater than or equal to 2 and less than n would have to be tested to see if they divided evenly into n, making the expression for the amount of iterations needed to factor n in this project n minus 2. In the case of decryption through logarithmic properties, 10 to the log c times d power minus m, all divided by n, iterations are required to acquire d. Because the formula for solving for d through logarithmic techniques can be simplified to d is equal to the log of n times n multiplier plus m divided by the log of c, n multiplier can be isolated and solved for to attain the number of iterations it would take to solve for d. So, if d is equal to the log of n times n multiplier plus m divided by the log of c, then d times log c is equal to the log of n times n multiplier plus m, and then 10 to the d times log c power is equal to n times n multiplier plus m. So 10 to the d times log c power minus m is equal to n times n multiplier, and thus n multiplier is equal to 10 to the d times log c power minus m all divided by n. By solving for n multiplier, the amount of iterations needed to calculate d through logarithmic techniques has been calculated to be 10 to the d times log c power minus m all divided by n. After I explored the mathematical intricacies of different decryption techniques in RSA encryption, and after I derived the amount of iterations necessary to carry out decryption using either decryption method, I decided to code what I had learned with Python. On the screen, you see some pictures of some of the coding that I did. Basically, what that coding did was calculate the decryption key using either of the methods that I explained, and that calculated the amount of iterations needed to calculate D in either instance. And here's some pictures of the graphical user interface that I created to provide any potential user of my program with a clear platform for understanding the decryption methods used in RSA encryption. I also created 5 educational videos to help people learn about decryption methods, which I've incorporated into my graphical user interface, because it's my hope to help people learn about a subject that's incredibly relevant in the world today, but isn't very well understood by many because of its difficult mathematical intricacies. Thank you for listening.